Hello, my name is Conor Hennessy, and I'm a graduate student at the University of Washington with the Evans School of Policy Analysis and Research Group.
Hi, my name is Andrew Towns. I am also a graduate student at the Evans Policy Analysis and Research Group.
We will be presenting submission number 128 for the 2020 Data for Policy Conference, titled Assessing Progress Towards Development Goals, Data Source Trade-Offs and Complementarities. There has been much excitement in the international development community about novel sources of data to measure progress towards development goals. Example applications include everything from using Twitter data as an early warning system for spiking food prices to using satellite imagery to predict poverty around the globe. Such novel data sources can be paired with novel computational approaches, such as machine learning, which automate the processes by which data can be analyzed for patterns in order to make predictions. Such data and methods have the potential to be more cost-effective and available more frequently than traditional data sources. And there is simply so much data available now. The vast majority of the data that exists today has been created in the past few years, 90% of it since 2017. Despite the excitement around novel data, there are challenges in addition to opportunities. Many have cited growing concerns about data privacy and ethics, as well as unequal access to novel data and technically complex tools such as machine learning that can exacerbate global inequities. However, less well examined is the question of how to think about the trade-offs and potential complementarities between more traditional and novel data. For example, while data may be available in real time at low cost, will the data source be able to provide information at the level of detail needed for a particular purpose? Is it possible to disaggregate by subpopulations of interest, such as women and migrants? If not, is there the potential to obscure unexamined bias? Our goal is to provide a framework for assessing such trade-offs between traditional and novel data to support decision makers seeking to measure progress towards development goals. Our work seeks to help fill this gap by developing and testing a framework for how development decision makers can examine trade-offs between traditional and novel data. Specifically, we explore the following questions. First, we explore the various types of traditional and novel data sources used in development to better understand the menu of options available to decision makers. Second, we looked into the literature on data utility and quality to understand how data sources can be assessed. And finally, we wanted to apply this framework to a case study application in order to examine the implications of data sources and analysis choices. To answer these driving questions, we did the following. We searched the literature for sources on novel data and machine learning in the context of international development, especially as it relates to food and agriculture. This resulted in two outputs, a typology of data sources that distinguishes between traditional and novel data, and a conceptualization of the dimensions of data quality and utility. Together, these two outputs constitute a framework for development decision makers to use in assessing data source trade-offs and potential complementarities, and therefore an opportunity to make more informed decisions about measurement. We then apply this framework using a case study relevant to the Sustainable Development Goals. Here, a typical traditional data source is household surveys, and a common novel approach is machine learning analysis of satellite data. We compare the utility and quality of these two data sources using our framework and examine the potential implications of choosing one data source over the other. First, we present our framework. On this slide, we see our categorization of data for development sources, which distinguishes between traditional and novel data sources. Traditional data sources include those that have traditionally been used, such as household surveys, administrative data, such as government records, and census data. Novel data sources include a diverse and growing range of data types from recent technological advancements and trends. This includes sensor data, such as that from satellite imagery, or scientific sensors, such as weather stations. While satellite imagery has been around for some time, recent gains in precision, affordability, and access and image processing have resulted in its increasing utility to development actors. Other novel data sources include crowdsourced data, often collected via mobile apps or text messages sent to a population being studied. Another source is the Internet of Things, which links physical devices such as health monitors, smart water meters, and even tractors to the internet, providing data for a variety of development applications. Finally, a growing category of novel data sources is social media data, including Twitter data and internet searches, which can be used to construct and analyze a variety of development indicators. While not at all exhaustive, this typology provides a helpful framework that can be used to examine key differences between our familiar, traditional data sources and novel data sources that many believe have great potential if benefits can be maximized and challenges minimized. Next, we identified dimensions of data utility and data quality, drawing on conventions in data science and statistics. For data utility, we identified 4 dimensions. Access and availability is the degree to which data are able to be used, which is low, for example, if data from certain businesses is proprietary or using the data is complex and requires special training. Cost refers to the financial and time costs associated with collecting data, such as that for equipment, training, time, materials, and labor. Timeliness is when data are collected at the specific time and frequency in which they are needed, as well as the time from data collection to decimation. Finally, coverage is the ability of data for the universe needed, either the sample or population. For example, that data are available for all needed geographies, subpopulations, that data are nationally representative, etc. Together, these dimensions allow us to assess the utility of data from different sources. For data quality, we identified the following 6 dimensions. Accuracy and validity refers to data that are free of bias. They measure what they are intended to measure and give correct answers to the research questions for which they are used. Precision is the sensitivity of the measurements used. For example, meters are more precise than kilometers. And to be clear, in this context, precision does not mean the same thing as accuracy. One could give a very precise measurement in meters that does not actually correspond to reality. That measurement would be precise but not accurate. Consistency and reliability of data means that if a measurement is taken on the same data point twice, it would provide the same value both times. The completeness of data is simply the degree to which the data is without missing values. Integrity of data means that data is not changed after it is collected. And finally, unique data means that the same measurements of the same thing are only included once in the data set. So, data that rank highly in these 6 dimensions can be understood to be high quality.
Having put forth a framework for development decision makers to use in assessing the trade-offs and complementarities between traditional and novel data, we turn to an application of this framework. We apply our framework to a case study rooted in the Sustainable Development Goals. It isn't simply enough to assess whether population-wide poverty is decreasing, for example. The UN Sustainable Development Goals were crafted to ensure that populations at higher risk for underrepresentation and economic gains are included. We leverage existing data on some of these groups, women, minorities, smallholder farmers, etc., to analyze the trade-offs between survey and satellite data and measuring progress for these subpopulations of interest. Progress towards SDG targets is typically measured using a combination of surveys, agricultural censuses, and administrative data, although there's also been interest in novel data sources. We identified 2 prominent data source options for measuring indicators relevant to the SDG subpopulations of interest. For traditional data, we use survey data from the World Bank's Living Standards Measurement Study, and integrated surveys on agriculture, or LSMS-ESA. Our data from the 2016 LSMS-ESA wave in Malawi and Ethiopia. For novel data, we use a machine learning analysis of satellite data. Specifically, we adapt the code from Jean et al.'s 2016 methodology to examine how estimates of poverty are constructed from satellite images. Next slide. We hypothesized some trade-offs in data utility and quality across satellite and survey data. Our assessment indicates that satellite data sources dominate on most measures of utility. They are cheaper, they have broader coverage globally, and they are available more frequently or even continuously. However, survey data may have an advantage over satellite data in terms of access and availability. Satellite data vary between publicly available and proprietary, while also requiring challenging and technically complex analytical techniques due to their unstructured nature. For data quality, we focus on the important dimension of accuracy and validity. Crucially, in terms of accuracy and validity, there is potential of novel data sources, such as satellite data, to misclassify certain subpopulations that are of interest in the SDGs, such as women or migrant workers, which poses a potential threat to validity, but remains understudied. We used an existing satellite model to predict poverty at the census tract level, examine potential areas of bias, and look at what influences the model's predictions. To evaluate bias, we look at several demographic groups whose incomes are mentioned in the SDGs to see if they are significantly more likely to be classified in a certain way. We leverage existing data on some of these groups, women, minorities, smallholder farmers, etc., to analyze whether a satellite-based model will be able to successfully estimate incomes for this group when they are trained on national level data. Our methodology followed a previous study that estimated the feasibility of satellite predictions using features visible to aerial imagery that were also collected in survey data, such as roof or road material, nighttime light intensity, and distance to urban centers. The survey data provide an opportunity to train and validate models because they estimate the value of daily consumption for each household. These are averaged across communities to produce pixel values for the other features. To assess bias, we examine the variance in predictions across UN SDG demographics that were all reported in the LSMS surveys, as well as the accuracy of models when placing communities above or below the international poverty line. We found that in rural areas, more households are close to the $1.90 per day international poverty threshold, which means that the certainty of poverty classifications based on satellite data is significantly reduced. The model was 9 to 22% more likely to indicate that a poor neighborhood is not poor if the neighborhood is predominantly agricultural. Furthermore, the ridge regression used to predict community consumption has an R-squared value of 0.55 when using all communities, but only 0.3 when using rural communities, further demonstrating difficulty of estimating rural poverty using satellite data. What is visible to a satellite does not explain the variation in consumption in rural areas as well as urban ones. This conclusion makes sense as rural areas are mostly without electricity in the countries we examined. Thus, satellite models are unable to use differences in nighttime light intensity to compare incomes between areas. We find that there is no indication that satellite models will have any particular demographic group bias once rural-urban divide is controlled for. Several demographic groups are overrepresented in the rural population, however. Female-headed households, which are communities where a majority of heads of household are female, are more likely to be found in rural areas in Ethiopia, but urban areas in Malawi. Thus, the accuracy of satellite data when answering questions about women's incomes may depend on the demographics of women in the particular countries being studied, which should be of interest to researchers when assessing data sources. Minorities. You find that in both Malawi and Ethiopia, ethnic minorities are more likely to be found in rural areas. Thus, we expect satellite models will be less accurate for studying ethnic minority incomes than incomes in the population as a whole. Youth. We found no statistically significant relationship between the average age of household heads in the community and the community's likelihood of being rural or urban in Malawi. But however, we are more likely to be rural in Ethiopia, which again underscores the importance of knowing the validity and bias of data sources have for various populations and the demographic characteristics of the population being researched. Migrant workers. We find that areas where seasonal migrant workers travel to seek work are disproportionately urban. Thus, satellite data may actually provide greater insight than survey data into the incomes of migrant workers, as satellite data can be updated season by season and performs relatively well in urban areas. Thus, returning to the question of data source validity, our results show that validity of satellite data depends very much on the question it is being used to answer. To a researcher interested in changes in income or consumption between seasons within a year in towns or cities, satellite data can provide a reasonably accurate answer, and satellites can provide more timely estimates than surveys can. Such a researcher might be willing to trade a certain amount of accuracy for the ability to see seasonal dynamics and consumption changes. However, a researcher evaluating progress towards SDG 2.3, which aims to double production and incomes of small-scale producers, over the last decade would be especially concerned about the problems with accuracy in rural areas that satellite models have, and would not be as interested in within-year income changes, thus more likely to prefer to use survey data. Our results tend to indicate that since the strongest satellite visible indicators of income, such as nightlights, tend to be less reliable in rural and poor areas, satellite-based estimates of income will be less accurate in rural areas. Certain demographic groups, such as female household heads, smallholder farmers, and the poorest 40% of the population, are overrepresented in rural areas. While there are many trade-offs between satellite and survey data, researchers interested in these groups should be wary of the validity of satellite data for their purposes. More optimistically, satellite data has greater accuracy in estimating income and poverty in more urban areas and can provide updated data at greater frequency than surveys can, something that will be of interest to researchers studying changes in income and consumption within years. Another consideration is access and availability of satellite data and its analysis. A trade-off to consider when selecting data sources is that it takes training in computer programming to create or even use satellite models for poverty prediction. Thus, when including people from areas where access to computers or higher education is an important part of research, survey models provide a more inclusive way of obtaining and disseminating data. Finally, models using satellite data currently must be trained with ground truth data so that they can learn to make estimates. The variation we see in the relationship between income and poverty and factors such as gentrification and urbanization underscore that there is no universal relationship between satellite visible factors and income. Thus, satellite models will always rely on survey data in order to identify relationships. These two data sources can complement each other, therefore. Thank you very much for your time and listening to our presentation today, and we hope to be able to address any questions you might have at the live Q&A session.
Thank you all for watching.